Okay, hello. We're going to prove some facts about polynomials. And let's just say that all we care about ever are polynomials with real coefficients. So that's all I care about. So I don't want to, I like polynomials that look like, well, what I really like are polynomials that look like this, you know, where all the coefficients are integers. But if I really have to, I will accept, though I'm not happy about it, kind of disgusting polynomials whose coefficients are irrational numbers, like, you know, 5 pi x squared or something like that. I'm less happy about that. But what I don't ever want to talk about in this class, ever again, are polynomials whose coefficients are imaginary, such as I don't know, 5 minus I might be the coefficient of x cubed, you know, plus I x squared, you know, minus 3 or something. Okay, so I really hate this. I don't even really like this very much. I love this. And the sort of tragedy and wonder of this subject is that even if I only care about polynomials with real coefficients, I still need to be talking about complex numbers because many of these polynomials have roots which are in fact complex. Okay, so we will find that we will find that our polynomials often have complex roots, and there is a big fact about these kinds of polynomials, and that is that complex roots come in conjugate pairs. Okay, so you may have heard of this before. This came up in class today, and what we're going to do right now is we're going to prove this sort of slowly and methodically. And okay, here we go. First, I want to consider two generic complex numbers. X is of the form r plus si, z is of the form u plus vi, where r, s, u, and v are all real numbers. And I'm following along on this worksheet called Complex Roots Come in Conjugate Pairs, which you downloaded so you can sort of follow along. Okay, and now I want to talk about the complex conjugate. What is the complex conjugate? Well, I can give sort of a boring answer. It's the conjugate of any complex number. So the conjugate of a plus bi is just a minus bi. Okay, so this is not a totally standard notation, but some people use it. So there it is, right? Take any generic complex number. The conjugate is a new complex number where the real part is the same, and you've just flipped the sign on the coefficient, or you've flipped the sign on the imaginary part. Okay, so great. You can also make a picture of this. If you want to do this on the complex plane, then if you have, okay, I'm even drawing it as a vector because I think of complex numbers as vectors, as I said today in class. Well, if that's a particular complex number, a plus bi, here it is on the complex plane where this is the real axis and this is the imaginary axis, then what does the conjugate look like? Well, it's kind of just over here. So, alright, and I think there's actually something kind of deep going on here, and I might not be getting right exactly to the heart of it, but a complex number and its conjugate, well, they have this obvious kind of geometric relationship, which is the reflections over the real axis. But on kind of like a deeper level, they have the same real component, so that's, I think, obviously clear, that they both have real component A, but they also have the same distance to the origin. So they have the same magnitude, so to speak. There's kind of a name for that, but and they have the same angle. Okay, give or take a negative. These angles are the same because these triangles are congruent. And so, sort of in every respect that matters, they are kind of like the same thing. And a kind of a deep way of thinking about everything we're about to do is that real numbers can't tell the difference between a complex number and its conjugate. Okay, in other words, if you give me some real numbers, okay, take an equation for example, x squared plus 9 equals 0. Well, what are the solutions to this equation? 3i is a solution, of course, but so is negative 3i, and in fact these are conjugates of each other. And so because this equation is an equation involving just real numbers, all the coefficients of the polynomial are real, then it kind of can't tell the difference. Okay, so that's almost the whole thing, and so this is just a particular example, but more generally, as long as you stick to polynomials with real coefficients, and that is what we're going to do, then the claim is that that real polynomial can't tell the difference, or can only tell the difference give or take in negative, which is what we're going to see. Okay, that was like the kind of strange warm-up. Now we're going to do some tedium. So we have an entire page, and we're just going to kind of grind it out. Let's go. Number 1, this is a kind of a walks you through the proof, basically, right here. So here we go. Normally we do this live. It's boring live, so now it will also be boring, but you'll just be watching it on 2 times speed, so it will be exciting. Prove that the conjugate of a sum is the sum of the conjugates. Okay, well, in other words, take 2 generic complex numbers, x and z, add them up, and then take the conjugate. What do you get? Well, let's just do it. I have r plus si, and I'm going to add to that u plus vi, and then I'm going to take the conjugate. Okay, well, I already know that when I add 2 complex numbers, I just get a new complex number in which the real part is r plus u, and the imaginary part is s plus v. And now I'm going to take the conjugate. Well, the conjugate of this is just going to be r plus u minus s plus v. Okay, cool. Well, of course, that is true, but, well, okay, the sort of lame way thing to do is to just stop and observe that that's true. Maybe we'll just do it the lame way. And then, okay, separately or something, what is the conjugate of x plus the conjugate of z? Well, that's asking for the conjugate of r plus si and the conjugate of u plus vi, and what happens is you get r minus si and u minus vi, and so parentheses are being used inconsistently. This is just r plus u minus s plus vi. And so indeed they are the same. Okay, so that kind of completes step 1. The sum. What have we shown? We've shown that these 2 are equal by just cranking them out in general. Okay, so the sum of the conjugate, the conjugate of the sum is the sum of the conjugates. Okay, well it is also true. Here I think I have to write smaller. It's also true that this is step 2 that you're supposed to do. Prove that the conjugate of a product is the product of the conjugates. Okay, well let's just go. What is the conjugate of xz? Well, I take x, which is r plus si, and I multiply it by z, which is u plus vi, to take just 2 generic complex numbers, and then I'm going to take the conjugate of that. Well, when you multiply these together, okay, I'm sort of fast at this, so I'm just going to do it. The real part is going to be ru, and then when you multiply si times vi, you get svi squared, so it's minus sv is the real part. And then plus, what is the imaginary part? Well, you multiply s and u, and you also multiply r and v. So, okay, so it's rv plus sui. And then I'm going to take the conjugate. And, okay, so what is this? It's ru minus sv minus rv plus sui. I. Okay, now, so that was the conjugate of a product. Now let's take the product of the conjugates. So starting a kind of a new line now. What happens if I first take the conjugates and then multiply? Well, what's the conjugate of x? It's the conjugate of r plus si times the conjugate of u plus vi. And now we just do it. This is r minus si. And this is u minus vi. Okay, it's getting a little messy down here in the bottom of the board. But, okay, it's just going to work out, right? Because what happens? Well, you get ru. But now when you multiply negative si times negative vi, the negatives cancel. And so you just get svi squared. In other words, minus sv. Cha. But also, well, let's just do it in one step so we finish it off. I get a minus su, and then also a minus rv. So this is indeed minus, factoring out the negative, rv plus su. Okay, so I have just showed by sort of careful algebra, brute force, definition of I, knowledge of how to multiply complex numbers, careful algebra, definition of the conjugate, that the sum of the conjugate is the conjugate of the sum is the sum of the conjugates, and the conjugate of the product is the product of the conjugates. Alright, that was the last, hard one, and now they're all just kind of easy, because we get a sort of new theorem, something like this, Theorem 3. What's Theorem 3? Theorem 3 says, prove that the conjugate of a square is the square of the conjugate. Okay, so you have a couple of options. If you want to do something with the conjugate of a square, the sort of slow thing to do would be to take this arbitrary x, r plus si, square it, take the conjugate, multiply this all out, blah, 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 blah. You can do that, and you will see that it's right. But if we want to sort of make use of previously proved theorems, then the most efficient thing to do now is to say, okay, well, if I want the conjugate of x squared, I'm going to use the definition of x squared to think of this as just x times x. And so x squared is really just a special case of the product of two numbers. We already have a theorem, Theorem 2, which says that the conjugate of a product is the product of the conjugates. Therefore, this is the conjugate of x times the conjugate of x, which is again, therefore, then just the conjugate of x squared. Okay, that's kind of exciting. Okay, and there's sort of no stop to this, right? What if I want the conjugate of a cube? The conjugate of x cubed. So an arbitrary complex number, if you cube it, then take the conjugate, what do you get? Well, I may rewrite x cubed as x squared times x. And now, once again, multiplication is sort of fundamentally binary. So you're never really multiplying three things. You're multiplying only ever two things at a time. And so the natural thing to do is to think of x cubed as being x squared times x. But now I'm just applying rule 2 again, which says that the conjugate of a product is the product of the conjugates. And so this is the conjugate of x squared times the conjugate of x. But now the conjugate of x squared is, by the previously proven rule 3, just the conjugate of x squared times the conjugate of x, and that is therefore the conjugate of x cubed. Okay, so the conjugate of a square is the square of the conjugate of a cube is the cube of the conjugate, and yeah, just more generally, one may use an advanced technique called induction to show that in general, the conjugate of the nth power of a complex number is the nth power of the conjugate of that number. But we don't actually need number 5. Well, we don't need number 5 for this worksheet, but we need it to sort of prove the general case. Okay, moving right along, take number 6. What's number 6? Prove that the conjugate of a real number is just itself. Okay, this seems kind of silly, but well, what does it even mean to take the conjugate of a real number? Well, you're just reflecting that real number over the real axis, so it's just itself again, right? Well, of course it is. Another way of thinking about it is if you accept that every real number is really just, or can be written as, a plus 0i, which is the justification for why the real numbers are a subset of the complex numbers, then this is just a minus 0i by the definition of conjugate, but of course that's just a again. Okay, that was 6. Now we're at 7. There's just a whole bunch of little things that are all just kind of boring, right? What's the conjugate of some, and now let me add a note, because A, B, and C are appearing for the first time. Well, back in step they did. A, B, and C are also to be interpreted as real numbers for the purposes of this worksheet. There, and I guess D too, because I think there's a D coming up. In other words, these are going to be my coefficients, my real coefficients, because I said at the beginning that that's all I care about. So okay, what's the conjugate of Cx? Well, okay, what I now do is I apply rule 2, which says that the conjugate of Cx is just the conjugate of C times the conjugate of x. But now, the conjugate of C, C being a real number, is just C times the conjugate of x. Okay, well, oh no, we're not on 8 yet, because 7 is like a kind of a combo of them all. Well, what else did I do? How about a sort of generic quadratic term? That's essentially what we're doing now, right? This is kind of a generic linear term with a real coefficient and a possibly complex variable. This is now a generic quadratic term. Well, once again, I should think of bx squared as just b times x squared. Rule 2 says that that's just the conjugate of b times the conjugate of x squared, but the conjugate of b is just b, and the conjugate of x squared is by rule 3, that, and so we get b conjugate of x squared. And, okay, last one, what about ax cubed? So in other words, a generic cubic term. If you take the conjugate of a generic cubic term, you get, once again, thinking of this as a times x cubed, it's just, by rule 2, the conjugate of a times the conjugate of x cubed. So that is the conjugate of a is just a, and the conjugate of x cubed is the conjugate of x cubed. Alright, what is going on here? This is building up to Rule 8. And Rule 8 says, okay, what if I want to take the conjugate of an entire cubic expression? So take an entire cubic expression, a generic one, ax cubed plus bx squared plus cx plus d, and take the conjugate of that entire thing. A, B, C, and D are real, but x is in general complex. Then what do I get? Well, once again, 4 things are being added. But okay, really you don't ever add 4 things, you add sort of 2 things at a time. So by repeated applications of rule 1, which says that the conjugate of a sum is the sum of the conjugates, here I can break up the conjugate of this sum into a sum of a bunch of conjugates. So I hope you will agree that this is just a x cubed, conjugate of x cubed plus the conjugate of bx squared plus the conjugate of cx plus the conjugate of d. But now, by rules 6 and 7, we see that this is just a conjugate of x cubed plus b conjugate of x squared plus c conjugate of x plus d. Okay, and alright, now I think we need to kind of pause for reflection or something. This was the whole goal. The whole goal of this worksheet was to get to this point. And now, okay. Well, what now? Now, what is this sort of theorem in number 8 really telling me? What it's telling me is, suppose I have some function. Let me call this function f. What does f look like? Well, for example, it might be 4x cubed minus 5x squared, I don't know, plus 7x plus 1, say. That was just a nice generic cubic that I just pulled out of nowhere. This theorem applies to any polynomial with real coefficients, and not just cubics, but okay, we are sticking specifically to polynomials with real coefficients. And I'm just going to use this particular cubic as an example. Well, if I really take to heart what just got proved in step 8, what this means is now if I plug some complex number in here, so let's say 3 plus 2i. Okay, so if we were doing this live in class, I would now ask someone to get a calculator or something and do this, but I forgot. And okay, so I'm just gonna do this right now. I don't even know where to go. Maybe Desmos. So let's just go. I wonder if it will even let me do complex numbers. I think so. Yeah, sure. No. Well, that's terrible. We're gonna keep this video going because I'm on a no edit type policy. Perhaps GeoGebra is the better place to go. Yeah, I'm gonna leave. I could just take out a calculator, but that's sort of lame. Well, here we go. Graphing calculator. I wonder if they will let me use complex numbers. 3 minus 2i. Yeah, I think GeoGebra is just smarter. Okay, and now I'm gonna make a function, and you can't see anything I'm doing right now. Well, if I want to be super, this is terrible, but it's not unprecedented for me to, this is an extremely terrible operation I have going on here, but since this is really only like a sketch, you may or may not be able to see what's going on here, but you may zoom in or something, and you're going to see what I am doing. Maybe I'll zoom in. There we go. 3 minus 2i. And now I just have this, function. What's my function? 4x cubed minus 5x squared plus 7x plus 1. That's my function. Boom. Okay, well now let's just see if it will let me do this. It's a good program, it will let me. Boom. Okay, notwithstanding some kind of strange rounding error, please let the record show, and I shall even write it on my whiteboard, that the answer, when I plug this particular complex number, I did minus. I was supposed to be doing plus. Well, this kind of ruins the suspense a little bit. Let me change the problem to minus. So, suppose the generic complex number I think of is 3 minus 2i. Well, according to technology, which is merely saving us time, I could do this myself, but it would just be tedious. When you plug 3 minus 2i into this polynomial, you just get back negative 39 minus 138i. Okay, that is very exciting. But now comes the key moment of truth. What happens if I plug in 3 plus 2i? Wow. Oh. Negative 39 plus 138. Okay. Let me go up here. Okay, that was fun. Yeah. Oh man. Alright. Well, zooming back out all the way and refocusing, what just happened here? Well, notice what really 8 is saying. What 8 is saying is that the conjugate of an entire cubic expression is that same cubic expression of the conjugate. And so, when I am plugging 3 minus 2i into this function, and I get back a certain thing, negative 39 minus 138i, what should I expect happens when I plug in f of 3 plus 2i? Well, 3 plus 2i is the conjugate of 3 minus 2i. And so if we believe this theorem number 8, which we just proved, and we should, what I get back when I plug in 3 plus 2i is, let's think of, I guess here we will think of the conjugate, we will think of x as being 3 plus 2i, yeah, and we'll think of the conjugate of x as being 3 minus 2i. And so the first thing I did was to take my function and plug in the conjugate, and I got a certain something. right? But now when I plug in 3 plus 2i, what happens? Well, according to this theorem, what I get is the conjugate of what I get when I plug, sorry, I lost my train of thought. When I plug in 3 plus 2i, I should get, oh man. So wait, this is, give me 1 second, it's x, yeah, so this is the negative 39 minus 138i, and now, what happens if I plug in x? Oh, well, okay. So when I plug this in, I'm going to get, the conjugate of that is equal to, the conjugate of this whole thing is negative 39 minus 138i. Okay, this is a terrible explanation. Let me just back up again. Basically, all this Theorem 8 says is that, if you plug some complex number, I think it's better if we just keep it sort of normal. If you plug in some complex number into a function, you get a certain something back. Okay, so the certain something we got back was negative 39 minus 138i. Okay, great. So here I'm back to thinking of x as just 3 minus 2i. I was confusing myself. Now, if you plug in the conjugate of that number, well, what happens? Yeah, what happens if you now plug in the conjugate? Well, the conjugate of, okay, when you plug in now x plus, when you let the conjugate of x, which is 3 plus 2i, when you plug that into the polynomial, so that's this thing here, what do you get? What you get is the conjugate of what you get in when you plug in 3 minus 2i. Sorry, I don't know why I had so much trouble saying that just then. But that's actually just what Theorem 8, this Theorem 8 says, right? You plug a certain number in, you get a certain thing back. You plug the conjugate in, what do you get? What you get is the conjugate of the previous result. And so here, when we plug in 3 plus 2i, we plug in 3 minus 2i and we get this. If we plug in the conjugate, what are we going to get? Answer, the conjugate of what we got before. And so in other words, this is going to be the conjugate of negative 39 minus 138i. In other words, what we get is negative 39 plus 138i, and that's exactly what the video showed. Okay, so I started this video by saying that sort of real coefficients, real polynomials with real coefficients kind of can't tell the difference between a number and its conjugate. That's not quite true, but what you end up with is what the sort of the deep theorem here, what this is really saying is that when you evaluate a polynomial with real coefficients at a complex number and its conjugate, what you're going to get back are two numbers which are conjugates of each other. And so they have the same real part, they have the same radius, and they have the same angle and the same everything. Okay, the grand conclusion of this whole worksheet, the thing I suppose really care about, is suppose you give me, let me try to stick to the notation on the worksheet. Suppose you now give me, this is now sort of number 9 at the very bottom, if you give me some polynomial, ax cubed plus bx squared plus cx plus d, where a, b, c, and d are real. And now, just let's suppose that you plug something in, like, I don't know, 4 minus I or something, and what you get back is 0. Well, if when you plug in this number and you get back 0, that's just another way of saying that 4 minus I is a root. Well then, what should happen when you plug in 4 plus I? This is now just a special case of Theorem 8. What we've seen in Theorem 8 is that when you plug in the conjugate of a number, what you get back is the conjugate of what you got when you plugged in the original number. But of course, the conjugate of 0 is just 0. And therefore, whenever 4 minus I is a root, 4 plus I has to be the root also. And that is why complex roots come in conjugate pairs. So as long as you start with a polynomial with real coefficients, and that's all we're ever going to do, then you sort of have this fact. Okay, that is, I think, clear now. Sorry that was 3 or 4 minutes longer than it needed to be. because of a temporary pause, I will say now that you have a homework assignment, and your homework assignment is to do this all over again by yourself with a kind of a different system. And the different system is now flip to the back of this worksheet, and you'll say, okay, let P be a polynomial with rational coefficients. Okay. So that just sort of rules out that rules out polynomials with, like, you know, kind of disgusting coefficients like this. Those are polynomials that we more or less ignore anyway, because we don't like them. So ignoring those, but sticking to just polynomials with rational coefficients, then we can make a similar claim to the one we've made above. And that is, this is a kind of a bad worksheet, I'll put that down. What that claim is that if when you plug into that polynomial some, I forget, oh man, I think I don't want to confuse you because on your thing, I think, yeah, q plus r root s. Okay, so if you plug in q plus r root s and you get back 0, then p of q minus r root s is also 0. This is the conclusion of the theorem of the back of this worksheet, that if q, r, and s are all rational numbers, then anytime you have a root of this form, then the number of this form is also a root. And basically you just do the exact same thing, right? You take a kind of a generic number of the form q plus r root s, and you define the conjugate of that number to be q minus r root s, and then you show methodically that that for generic numbers of this form with the same kind of root s, that the sum, that the conjugate of the sum is the sum of the conjugates, and that the conjugate of the product is the product of the conjugates, etc. And by reconstructing all the logic, there's a couple of details to work out. By reconstructing the logic, and I think here, I can't remember, I'm looking at it now. Here I said z should be 2 plus t plus, z should be t plus u root s. So I'm just getting more and more letters here, such that the conjugate of z would be t minus u root s. So sort of if your numbers are all in the same kind of like square root or something, then this holds, and then you just sort of do it and you get the exact same thing. Okay.